In the last lecture, we learned how an electrostatic field applied to the cathode or to a piece of metal can extract electrons. That is known as field emission, and we also discussed the field effect displays for the modern televisions. Then we came to the important topic of photoelectric effect, important phenomenon of photoelectric effect, and we found that in this phenomenon waves behave like particles. Each particle carries energy h nu, and if this energy h nu is higher than the work function, then the electrons will be emitted, otherwise electrons will not be emitted. And once the frequency is higher than this threshold frequency, intensity has no effect on the emission of electrons. The current increases, but the lower frequency electrons will not emit even if the intensity is very high. And we also found that the quantum hypothesis, that is, the wave carries energy as a bundle equal to h nu and delivers energy instantly to the electron in the cathode. This quantum hypothesis allowed us to explain the photoelectric effect. We have seen earlier that we see in the last lecture, we saw that in certain phenomenon electromagnetic waves exhibit particle like behavior, right, just like the photoelectric effect. These waves deliver energy to free electrons in metals in the form of packets of energy or photons. The quantum of energy carried by a photon is h nu, E equal to h nu. Because of the mass energy relation, you see Einstein has relation that energy is equal to mc squared. So, therefore, if I divide this by c squared, I will get the mass of the photon, and the mass of the photon is h nu by c squared, and mass times the velocity mc gives me the momentum of the photon, and that is h nu by c squared mass into the velocity, which is h nu by c, and the one can write this as h by lambda. So, the relationship between the momentum and the wavelength of light, if we go by photoelectric effect, it is h by momentum is equal to h by lambda. Incidentally, we also have this relation from special relativity, that the mass of a particle is equal to its rest mass divided by 1 minus v squared by c squared under root. You see, if v approaches c, this quantity becomes very small, and therefore, the mass of the particle increases. However, for the photon v is equal to c. So, therefore, this denominator becomes 0, and therefore, it is necessary that the quantity m 0 also becomes 0. Otherwise, if this is not 0, then it will become infinite. So, m 0 must also be 0, that is, the photons do not have a rest mass. M 0 is rest mass, photons do not have a rest mass because they move with velocity c. And it also implies that the photons cannot be at rest, because if they do, then this again becomes 1 and the mass of a photon becomes equal to m 0, but mass of the rest mass of the photon is 0. Therefore, it also implies that photons cannot be at rest. Photons do not have a rest mass, and photons cannot be at rest. They must always be moving. Let us take a few examples to consolidate the various ideas that we have discussed. In an experiment on photoelectric effect, light from a 10-watt UV lamp is one which emits ultraviolet radiation, emitting photons of wavelength 365 nanometers is incident on the cathode. The stopping potential is found to be 1.32 volts. Find the work function of the material of the cathode. Incident light is then changed high intensity red light. This is ultraviolet light, but low intensity 10 watts. Then we change the high intensity red light from helium neon laser. Would we still get photoelectrons? That is the question. How do we find the answer? All right. You know this equation, remember this equation, EV0, that is the energy, kinetic energy of the photoelectron, is equal to h nu minus h nu 0, where h nu 0 is the work function. So, given the data we will find the work function, because V 0 is given, stopping potential is given, h we know, frequency is given or wavelength is given, does not matter. So, we can find h nu 0, the work function, and see if the red light provides energy greater than the work function. If it does, then it will be able to extract electrons. If it does not, then no electrons would be emitted. So, that is all we have done. We write the above equation as this in terms of the wavelength h nu h c by lambda minus E nu E V 0, substitute the values and get V 0 or the work function phi. Phi comes out to be 2.09 electron volts. The energy contained in a photon of red light, although intensity is very high, but the energy of each photon is h c by lambda, and if I substitute the value of lambda here, then which is 6.33 nanometers, then the 633 nanometers. Then we find that the energy of this photon is just 1.96 eV, which is less than this. Therefore, this high intensity red light will not be able to emit photoelectrons, will not be able to extract photoelectrons from the cathode. You see, this is 633 nanometers. Now, before proceeding further, let us see what are the phenomena which can be explained by waves, which can be explained by particles, and which can be explained by both waves and particles. So, we have listed the phenomena associated with light, and then we have tick marks for the possible explanation. Reflection is possible both on wave theory as well as on particle theory, on wave nature as well as particle nature. Refraction again possible to explain on wave nature as also on particle nature. You remember this, we explained reflection and refraction on the basis of Huygens principle of wave functions, the wave fronts advancing and each particle on the wave front becoming a source of secondary waves and so on. We did reflection and refraction on the basis of Huygens principle and saw that Huygens principle does explain the phenomena of reflection and refraction. Interference, we found only wave theory can explain interference, because the waves depending upon their phase difference will interfere either constructively or destructively to give us the interference pattern. Therefore, interference phenomenon can be explained only on wave theory, not on the particle nature of matter. Diffraction again can be explained only on the wave nature of matter, not by the particle nature of matter. Polarization again can be explained only on the wave nature of the radiation and not on the particle nature. Photoelectric effect we just discussed, this cannot be explained on the wave nature, but can be explained on the particle nature. Why? Because we need instant release of electrons. This instant release of electrons can take place only if the wave behaves like a particle carrying energy h nu, which is greater than the wave function, the work function of the metal. Now, after this table, there is an important question which arises. And what is the question? If a wave can behave like a particle, does a particle also behave like a wave? We have seen that electrons, the electromagnetic waves are behaving like particles, photons. The question is the reverse also true? Does an electron, for example, behave like a wave? Does a neutron behave like a wave? Does a cricket ball behave like a wave? So, we will have to answer all these questions. So, before we answer these questions, let us briefly recount the interesting history of theory of light. You see, I have been pointing out to you whenever I got the occasion in these lectures, the nature of science itself, how theories change with time, how some theories are just thrown away, how some theories are modified and how some theories are improved, so that they can explain the newer observations. So, this is the nature of science, that nothing is final, everything is tentative. So, with that in view, let us briefly see how the brief history of the theory of light. You know already that Huygens proposed that light travelled like waves. Newton also proposed at the same time, or almost at the same time, that the particle nature of light. He said light behaves like particles. An experiment performed by Young, the two slit interference experiment, settled beyond doubt, at least at that time, the wave nature of light, because the Young's observations of the interference pattern could not be explained by the particle nature, and therefore, the wave nature was accepted. At least at that time, there was no dispute, there was no misgivings about the wave nature of light. And Maxwell's theory and Hertz's experiments settled the issue finally in favor of the wave nature of light. So, that is the brief history. I have already emphasized the tentative nature of scientific theories. However well entrenched the theories may be, they are subject to modification, improvement, or even abandonment altogether if new evidence comes to light. We are going to see another example. Towards the end of the last quarter of the 19th century, scientists were convinced that everything about nature of light was known, because Young's experiment was very successfully explained by wave nature of light. Then Maxwell did his work and showed that light is electromagnetic wave in nature, and Hertz's experiment showed the existence of the electromagnetic waves and so on. So, the matter was settled, and most scientists believed towards the end of the 19th century that everything about light was known. And as soon as they thought everything was known, there were problems. What were the problems? Soon, however, new problems cropped up. One of these concerned the nature of black body radiation. The wave theory, as we knew, could not explain the kind emitted by an incandescent lamp or burning charcoal, for example. In fact, all objects, hot or cold, emit black body radiation. I am also emitting black body radiation. This laptop is also emitting black body radiation. The difference only is in intensity. If we have a heated piece of coal, it also emits black body radiation. Again, the difference is in intensity. In fact, all objects, hot or cold, emit black body radiation. The only difference is that at higher temperature, the radiation is more intense. This I have explained many times, so I will just skip it, except to say that this played an important role in the revolution through which science went at that time. You know, this is black body radiation, this is the classical explanation, Rayleigh-Jean's law. This could not explain this phenomenon, and then Planck postulated that energy exists, the electromagnetic energy exists in the form of quanta, each of energy h nu. So, in the closing years of 19th century, Planck succeeded in explaining the nature of the complete black body spectrum, and he gave the idea of quantum, which, as we have been discussing, Einstein used in photoelectric effect to explain the photoelectric effect. So, this is the brief history of the light, and after this brief interlude, we return to the question. You know, we asked the question, if a wave can behave like a particle, does a particle also behave like a wave? And now we are in a position to answer this question, and the answer for the first time to this question was given in affirmative, that is, yes, it can be done, and the person who did it was de Broglie. He argued that nature cannot single out electromagnetic radiation for dual behavior. You see, we have found that electromagnetic natures sometimes behave, electromagnetic waves sometimes behave as particles, sometimes they behave as waves. So, he said, how can it be that electromagnetic waves can behave as particles and as waves? There must be other particles which can have waves associated with them. So, that is what he said. He said nature cannot single out only electromagnetic radiation for dual behavior. He proposed that even matter particles have dual nature, that is, they behave like particles as well as waves. Particles like electrons, protons, neutrons, even objects like cricket balls and trucks, they all have their wave part, their wave, so to say, face. The waves associated with matter are called in the memory of de Broglie, they are known as de Broglie waves. We will find out the electron de Broglie waves, and if needed we can find the proton or neutron de Broglie waves, and I shall also calculate the de Broglie waves of the cricket ball. So, how did Broglie proceed? Taking cue from the quantum hypothesis of Planck and the expression for the momentum of a photon p equal to h nu, we have derived this already, p equal to h nu. He said he generalized this, that this is true not only of electromagnetic waves, this is true of particles also. Derived on the basis of photoelectric effect, de Broglie suggested that the wavelength of matter particles of mass m and momentum p is given by this. He said all particles can behave like waves, and the wavelength that will be associated with those particles would be given by h by p, p is the momentum, or h by 2 root of 2 m e, where e is the energy, and this is for non-relativistic particles. So, he said that all particles have waves associated with them, and the wavelength is given by h divided by the momentum of the particle, or divided by the square root of 2 m e. This is known as de Broglie relation, and this is a very important relation, the development of quantum mechanics. So, if matter particles really exhibit the wave phenomenon, how do we observe them? He said that there are waves, then we must find ways and means of observing them. You remember that once I pointed out that each theory must predict what its consequences can be, and if those consequences are observed, then the theory is accepted. If those consequences are not observed, then theory is not accepted. So, de Broglie had this theory that each particle has wavelength h, wavelength lambda given by h by p, but unless this is observed, one cannot accept this relationship. So, the observation of this phenomenon was very crucial. Here is the animation. You see, as particle moves, there are waves which are associated with the particle, and they move along with the particle. This is an animation. And you see, also notice that if the momentum of the particle is high, then its lambda is low, because it is inversely proportional to the momentum. So, if the particle has higher velocity, higher momentum, then this wave spread would be smaller, the wavelength would be smaller according to the Broglie relationship. Let us take an example. Let us calculate the wavelength of an electron moving with 1/10 the speed of light. Now, solution, let us use the de Broglie relation, lambda is h by p, p is mv, and m of course we know, electron 9.1 10 to the power minus 31 kilograms, and velocity is 1/10 of the velocity of light. So, 3 into 10 to the power 7. So, if we plug in the numbers, we get the wavelength of the electron with this kind of energy to be equal to 10 to the power minus 10 meters. This is the size of an atom. So, the electron does have a wave according to de Broglie relation. We have not yet verified the relation, but if we accept that relation, then electrons have waves whose size is of the order of the size of the atom. For comparison, we also calculate the wavelength of a cricket ball moving at a speed of 150 kilometers per hour. This is the velocity with which really fast bowlers deliver the ball. If you are a fan of cricket, you would know that the very fast bowlers these days, they throw balls, they bowl with a speed of 150 kilometers per hour. The mass of the cricket ball varies. from place to place, but it is around 160 grams. So, we shall take that as the mass of the cricket ball. So, the wavelength of the ball would be h divided by the mass of the ball and the velocity of the ball. Velocity of the ball converted into meter per second is 41.7 meters per second. Mass is 0.16 kilograms. This is the value of h. So, if we calculate this, this turns out to be 10 to the power minus 34 meters, and it is so small. In this case, it was 10 to the power minus 10 meters, and in the case of ball, it turns out to be 10 to the power minus 34 meters. It is very, very small. That is why we do not see the waves associated with cricket balls. We shall see waves associated with the electrons, but not with cricket balls. But it does not mean that cricket balls do not have waves associated with them if de Broglie hypothesis is verified by experimental observations. We are now going towards that experimental observation, and therefore, I have taken this example. An electron is accelerated through electric potential V. What would be its de Broglie wavelength? So, after being accelerated through potential V, the energy of the electron would be qV, where q is the charge of the electron. Since momentum is given by p equal to square root of 2 m e, the de Broglie wavelength lambda would be h by p equal to h by 2 m times qV. M is the mass of the particle, in this case electron, q is the charge, and V is the potential difference through which the charged particle has been accelerated. Now, suppose V is 54 volts, you will see the reference to 54 volts later, but suppose it is 54 volts, then you find that lambda is 1.67 into 10 to the power minus 10 meters, or 0.167 nanometers. Remember this number, because this will be useful later on. Now, if the electrons or particles have waves, then how do we verify? We recall the phenomena that are explained only on the wave nature. And what are those phenomena? Interference and diffraction. So, we turn to these phenomena to find out whether particles like electrons have waves associated with them or not, whether particle like electron behaves like a wave or not. That is the objective. But where do we find, remember that interference and diffraction effects are seen only when the sizes of apertures are as small as the wavelength. Now, here the wavelength we found is 10 to the power minus 10 meters, of that order. Where do we find the apertures of that size? That is not possible. So, what do? We turn to something else, we turn to the crystalline structure, because we have seen already in X-rays that the X-rays are diffracted by the crystal, because the gap between these planes in a crystal, the atoms are very regular, arranged in a very regular fashion. The distance between these rows is fixed, does not change, and therefore, if this distance is of the order of the wavelength, say in this case X-rays, then we shall see the diffraction effects, and that is what we see actually. You see, these waves are coming, these rays are coming here, and this one is reflected from this atom and goes to this direction. So, therefore, the path difference between this and this is this red, this shown in red, these two, this one and this one. If we add these two, this is the path difference between these rays and these rays, and this path difference, this one, this red, this one is d sin theta, this red is also d sin theta, and therefore, the path difference between this and this is 2d sin theta. So, if we can find arrays of atoms like this, then we can expect X-rays to show diffraction, which they do. X-rays are now routinely used for determining the structure of various things. So, if the path difference is 2d sin theta, between this, and this path difference 2d sin theta is equal to a whole number of wavelengths, then we shall see waves interfering constructively, otherwise they will interfere destructively. So, when they interfere constructively, we will see the bright spot. So, in X-rays, if this is equal to say 1 lambda or 2 lambda or 3 lambda 2d sin theta, then these waves after reflection or scattering, they interfere constructively. This 2d sin theta equal to n lambda is known as Bragg's law. Interestingly, this Bragg's law was discovered by the team consisting of the son and the father, the elder Bragg and the younger Bragg. These two Braggs, they determined this, they found this Bragg's law, and the planes from which scattering or reflection takes place, they are known as Bragg planes. So, X-rays are these days routinely used to determine the structure of salts, minerals, metals and semiconductors. The experimental verification of de Broglie relation came through the experiments of Davison-Germer. By verifying de Broglie relation, this historic experiment played a very important role in the development of quantum mechanics, because this experiment confirmed the hypothesis advanced by de Broglie. Again, an interesting sidelight on how science works and how scientists work. Davison and Germer were working in Bell Labs in America. It is a very famous laboratory, but there they work on something different. Initially, they were not looking to verify de Broglie relation. They were perhaps not even aware of this relation. You see, those days the communication was not so efficient. These people were working in Bell Labs in America. All this work, de Broglie, etc., was happening in Europe. Of course, some scientists who are interested in quantum mechanics in America knew about that work, but these people perhaps did not, because they were working on something else. Their aim was to investigate the structure of nickel crystals, because they wanted to use these crystals in some other devices. Only later, on a visit to Europe, did Davison come to know of the de Broglie relation and of the possibility that their setup could be used to demonstrate the wave nature of electrons. See, Davison got an invitation from Europe to visit some places. I think he went to Oxford, and there he learnt about there was a discussion, there was a working group discussing the de Broglie relations, and there he came to know that such relation exists, and that the experimental setup that they have for determining the structure of nickel crystals can be adapted to verify this relation. And when he came back to America, the two of them, Davison and Germer, they modified their apparatus, whatever needed to be done, and then verified de Broglie relationship. In the next lecture, we shall see the details of the experiment done by Davison and Germer. We shall also calculate the wavelengths associated with the electrons when they orbit the nucleus, and we shall now be able to give some justification, advance some justification for the Bohr postulate that in stationary states the electron does not emit radiation and therefore does not fall onto the nucleus. And we shall derive this relation that in the nth orbit of the electron, the circumference is equal to n times lambda. Lambda is the electron de Broglie wavelength.